write any natural number, just write it like this. Then count the numbers of even, odd and total digits. 0 is an even digit. So, 0, 2, 4, 6, 8 and 1, 3, 5, 7, 9. Count the numbers of even, odd and total digits. In this particular case, you will be having 15 even digits, 16 odd digits, so obviously 31 total digits. So, you write these three numbers side by side, that is, you write 1, 5, 1, 6, 3, 1. So, now you have only one even digit 6 and 5 odd digits and total digit is 6. So, you write 156. So, one even digit, two odd digits is 1, 2, 3 and then one even digit, two odd digits. So, 1, 2, 3. So, this is what I mean by mathematical black hole. Now, it is independent of English. I am doing some iterations on natural numbers or positive integers. Write any number. I just take 25 because it's a small number. You can write anything. Then add the squares of the digits to obtain the next number. This is the iteration that I am defining. Add the squares of the digits to obtain the next number, which is obviously 2 square plus 5 square is 29. So, then continue the process. 2 square plus 9 square is 85. And if you continue this, you get this 89, then 145, 42, 24 and after 8 steps you get back 89. So, it is not a black hole, but there is some regularity that is periodic. It is 8 cycle periodic. This iteration does not show a black hole, but if you start from 25 it shows a 8 cycle periodic behavior. So, these are called attractors. I have seen now two kinds of attractors. One is a black hole attractor. Whatever you start from, all the numbers are is basin of attraction. You start from the starting set is the set of basin of attraction, constitute the basin of attraction, and where it lands, that I call attractor. It is either a fixed point or black hole or a periodic behavior. For example, this instead of 25 had I started from 86. So, it will land you to 1. Next step gives 1 and that becomes a black hole. But the story is that either you reach 1 or you reach 8 cycle periodic behavior. There is nothing else is possible. Whatever may be the starting point, there are two kinds of attractor. Each attractor has its own basin of attraction. Either you reach 1 or you reach a 8 cycle periodic behavior. You will definitely land in one of those 8 numbers. 89, 145, whatever it is, and wherever you land, then after 8 cycles it will keep on repeating. Just this is a nice thing. Write any natural number, only restriction is divisible by 3, not any, but divisible by 3. So, we write 21. Now, instead of squaring the digits, you take the cube of the digits and add them. So, 2 cube plus 1 cube is 9. Then continue this iteration, 9 cube is 729, 1080, 513, 153 and then, so if you start with a number divisible by 3, this iteration will land you to 153. In fact, there are only 4 numbers which are the sum of its digits of its own cubes, like 1 cube plus 5 cube plus 3 cube is 153. There are 3 such numbers, a trivial one I am not counting. There exist only 4 numbers, 2 others are 370 and 407. You see 3 cube plus 7 cube is 370 and 4 cube plus 7 cube is 407. There is no other number. There are a lot of students here. Can you give me the 4th number quickly? 3 I have given, 153, 370 and 407. The 4th one must be 371 because 1 cube will add you 1. So, write a 4-digit natural number using at least 2 different digits. That means you can write 1000, but don't write 1111. You cannot write the same digit all the 4 times, at least 2 different digits. So I write 1587, that is perfectly arbitrary, doesn't matter. Now you write the largest number using these 4 digits, that is 8751, and the smallest with these 7 digits, so it will be 1578, and take the difference, largest minus smallest. If you write all 4 same, obviously largest and smallest will be same, a difference will not be meaningful. Now continue this process. Once you reach 6174, that is the black hole. And this number, because I take it this example because this number is known in the literature by the name of an Indian, D.R. Kaprekar, who expired in 1986. Pune-based, I shouldn't call him a number theorist, but recreational number theorist. There are lots of numbers which are called Kaprekar numbers. This is one of the Kaprekar numbers, 6174. Okay. Now we go into a little more complicated kind of iteration, that I start with some number xk, and if it is odd, then the next step I get 3xk plus 1, and if it is even, then I get half of xk, and continue this iteration with any starting xk, any integer xk. So I start with just like that 17. So it is odd. So next number is 51 plus 1, 52, and it is even. So 26, it is even. So 13. It is odd. So 3 into 13 plus 1 is 40. It is even. 20, 10, 5. It is odd. So 16, 8, 4, 2, 1. 1 will give you back 4, 4, 2, 1. So you will get a 3-cycle periodic behavior with any starting number. This stable 3-cycle periodic behavior. Actually, this is known as Collard's conjecture. It was made in 1938, but it is still an open problem. Nobody has been able to prove it, that it has to do this. But with computer, that's a problem. People have tried with all initial starting values up to this number. Starting from 1 to 5.764 into 10 to the power 18. With all these starting points, you get 421, 421, 421. Actually, lots of study has been done. Sometimes, like if you start with 27, you have to test your patience, because only after 111 iterations you will reach 1. And the highest it will go to 9232, then it will come back. But it has, no exception has been found, sorry. No exception has been found. And these numbers are called, this sequence that is called hailstone numbers, because in a storm cloud, the hailstones drift upward and downward in a haphazard fashion. You see, it is going up, then down, down, then going up, down, 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 again going up. So drifting up and down in a haphazard fashion, ultimately reaching the ground 1. And after hitting the ground, an elastic collision jumps a little bit 4, then again to 1. So that's why these numbers are called hailstone numbers.
This is more similar to a stable limit cycle, because you have 3 states, 1 to 4, and it just revolves after a certain time instant. It just
right. Right.
It's a stable limit cycle.
Stable 3-cycle.
Right.
3-cycle because it after 3 iterations it's come to the same thing. So write a number, take the sum of all its divisor including 1. There are certain numbers which will give you, after this operation, the same number back. For example, if you start with 6, what are the divisors of 6? 1, 2 and 3. You add 1, 2 and 3, you get 6. So these are called perfect numbers. It is known from Euclid's time, but January 2018, the 50th perfect number has been found. Nobody knows whether perfect number continues forever or there are a limited number of perfect numbers. But 50th perfect number has been found only January of this year. Actually, there is a great internet prime search program, GIMPS, GIMPS. Lots of computers are connected all over the world. They are looking for Mersenne prime. And once you get a Mersenne prime, you get one perfect number. So, these are perfect numbers, first three. You see 6, 28, 496. If you add all this, you will get this number. So, these are black holes, right? Because you start from 6, you get back to 6. Now, can you have two cycles? I start from A, go to B, and if I start with B, come to A. Then it will be a 2 cycle. Period 2 cycle, these are called friendly numbers or amicable numbers. Like 220, these are the divisors of 220. You add them, you get 284. And divisors of 284 are these. And if you add them, you get 220. So, 220 and 284 are friendly numbers or amicable numbers. In fact, Pythagoreans are so excited with this, the definition of friendship became a friend is one who is the other I, such as 220 and 284. That means I chop you off, add the sum, I get your friend. And I chop your friend off and add the sum, I get you back. So, that is what the friendly numbers is. So, then there is an Arab mathematician, Thabit ibn Qurra, who even give a formula for generating such friendly numbers. But there is some trial and error, not that from the formula you can go on generating. You have to go through a lot of trial and error. This was not known to the European. So, Fermat, this was known to the Greek, and Fermat in 1630s gave 2 more friendly numbers. And that was a great achievement. I have got a pair of friendly numbers. And because Fermat got it, Descartes had to get it, because Descartes and Fermat were competitors. Fermat was judge and Descartes was a scientist. So, Descartes never gave Fermat much importance, but Fermat was genius. So, Descartes said, I have also got a pair of friendly numbers. So, these are friendly numbers, fine, I mean people have to stop, but then came the great genius Euler, listed 60 such pair of friendly numbers. In 1750, first he gave 30, 1747 I think, and 1750 he added 30 more. He gave 60 such pair of friendly numbers. I think that is where the fever stopped. People did not want to do anything more. But all these great geniuses missed these 2 small numbers, 1184 and 1210. This was found by a 16-year-old school student in Italy. All these, because they were looking for generating a hidden formula. Nobody will tell the formula, I have got some pattern and then I will try to generate. But these 2 numbers come out of that pattern, so they missed it. But if okay, I do not go for friendly numbers, but can I find sociable numbers? Like 5 cycle, that if you start from here, add the factors of this, you get this, add the factors of this, you get this, this, and then this, and add the factor of this, you will get back. So, these 5 numbers are called sociable numbers. But I thought sociable numbers of 5 numbers are all right, but yesterday I made that comment, mathematicians do not seem to have much work. So, they do not stop. They also got period 28, highly social, I mean really party people. But most of the times if you get to a prime number, then it will give you 1. If after adding the factors, if you arrive at a prime number, in the next step you will get only 1, because there is no other factor. So, lots of different attractors and basins of attraction that I am trying to arrive at. Okay. So far we are doing over integers. Now, let us expand the field, that I do define an iteration process, but do it over all the real numbers, not just integers. Let us now consider iterations with real number, which is continuum. So, Professor Sternberg of Harvard, he says, let us talk of the earliest iteration which has been recorded in the history of mathematics. That was 2000 BC, that is almost 4000 years ago, in a clay tablet, Babylonian clay tablet, with the cuneiform they used to write, and they had an iteration process for determining the positive square root of a positive integer. You are given an positive integer, find the positive square root through a process of iteration. They did not know how to take the square root. So, this is the iteration. I want to find the square root of a. So, I start with any xk, then in the next step I get this, which is half of xk plus a by xk. Okay. That is the iteration that was noted. And how good it is, let us see just with an example. For a equal to 2. So, what is the first iteration? Because I am very poor in computation, I think square root of 2 is 99. Square root of 2, I take 99. Then I continue the iteration, and after 11 iterations I get this, which is correct to 11 decimal places. Even with a starting point as bad as 99, within 11 iterations, 10 iterations or 11 iterations, we are getting 11 decimal places correct. So, it is a very nice formula. Now, today how will you get this formula? All you first know Newton's method of root extraction of a polynomial by iteration. So, I am looking for the roots of this polynomial x square minus a equal to 0. So, xk plus 1 starting from xk, if I do h and then do Taylor's expansion, you get h equal to this. So, if you put this value of h, you get that formula. Now, the question is that Babylonian time they did not know Newton's formula or calculus or derivative or that, how did they arrive at? I think, I do not know, nobody told me, but I think they get it as simple as that, that if I put xk equal to root a, then this is root a, this is root a, this is half of 2 root a, so I get root a. So, root a is a fixed point. If I start with root a, I get back at the first iteration root a back. So, root a is the fixed point. Now, iterations to converge, what he says, that if I have underestimated the root a, if xk is less than root a, then this is more than root a. So, if you take the average, you are going to moving towards root k, and if it is less than root k, then this is more, if it is more, then this is less. So, every time you are moving towards the root k, maybe that is how they arrived at it. So, it is very simple, looks like that such iterations on continuous real number is very good, but we will see how complicated it can become, because this is what is done on simplest model of discrete dynamical systems, which are dynamics means some physical variable x which is continuous, is a function of time, but I measure x only at fixed time intervals, not continuously at t1, at t2, at t3 like that, and at any time instant the value is related only to the previous value. So, xk plus 1 is fxk. This is a simplest dynamical systems, discrete dynamical systems or 1D map. So, that square root process is nothing but a 1D map, and it behaved very nicely, but the trouble is it does not behave so nicely every time. Let us consider a very simple 1D map like this. Xk plus 1 is 1 plus 1 upon xk. Only thing, xk cannot be 0, because if it is 0 then it blows up. So, what is the fixed point? Fixed point means if I start with x star, I get back x star, then x star is the fixed point. So, for black hole or stable fixed point, x star is 1 plus 1 upon x star. This is the simple quadratic equation for x star. I can solve for x star. I get 1 plus root 5 by 2, 1 minus root 5 by 2, which is plus and this minus. Now, the question is, if there are two fixed points, which one will be attained, right? In the previous one there was only one fixed point, root A, so no problem. Here there are two fixed points, which one will be attained? Initially it may appear that it will depend on your initial guess. What is the basin of attraction of those fixed points? One will take you to x1 star, other may take you to x2 star. So, with my simple logic, I started with 2 expecting I will get the positive root and started with -2 expecting to get the negative root. But my expectation was totally wrong. In both times it is trying to x1 star, 1.618, no, there is nowhere negative. So, x1 star and not x2 star is the black hole. So, we have to talk of what is the stability of a fixed point. You just not only look at a fixed point, you have to also talk whether it is stable. That means stable, fixed point is all right, but if I disturb it, does it have a tendency to come back towards the fixed point or go away from the fixed point? Disturbance grows or disturbance decays or oscillates maybe. So, x1 star is fxk, the fixed point x star is fx star. So, give a disturbance delta and then fx star delta, if I do Taylor's expansion I get this. So, if after one iteration the deviation from the x star is this, and then this must be modulus of this must be less than 1 for stable fixed point and modulus of that should be more than 1 for unstable fixed point. So, this is the condition. So, with that condition we find that this is the only stable fixed point, other one is unstable. So, whatever you start value, you will always end up in this 1.618, sorry. Except these points, because if you start with -1, then first iteration will give you 1 plus -1, which is 0, and 0 is not allowed, it will blow up. So, if you start with -half, you will get -1, then it will blow up. So, from all these infinite set of points, it will blow up, it will not go to the fixed point. So, these points, for a better want of a name, let us call white holes, because black holes attract and white holes repel, that is what I mean, there is nothing like white hole. So, all these are white holes. So, and you look at this, these are negative of the ratio of the 2 consecutive Fibonacci numbers. With such starting points, iterates blow up to infinity, and at the end of it, if you do it, it tends at the as you know 2 Fibonacci ratio of 2 consecutive Fibonacci numbers as n goes to infinity is x2 star. So, x2 star is fixed point, but if you disturb it, it takes infinite steps to blow up. Now, consider another iterate, xk plus 1 is x square minus 1, which is very similar to the previous one. Only thing xk has to be limited here, otherwise everything is white hole. You can know, if you start with xk equal to 2, then 2 square minus 1 is 3, then 3 square minus 1 will be 8, it will just blow up. So, all will be white holes. If xk lies within this range, then it will not blow up. So, fixed point we can say this, we get the same 2 fixed point like the previous one, but here both are unstable, because now we know how to check the stability. You have to take the derivative of this function and evaluate it at the fixed point. So, derivative is 2xk. So, if you take the fixed point, 2 into this is 3 point something and 2 into this is minus less than -1. So, both are unstable. Then what happens? If both fixed points are unstable, then what happens? It is not attracted to either. So, being an engineer, take out the calculator and start calculating before I make a guess. So, we start with 2 starting point, 0.321 and 0.322, and evaluate these iterations. Let us see what happens. After this I see it oscillates between 0 and -1, -1, 0, -1, 0 and -1, 0, -1, 0. It will continue forever. So, there is no fixed point, but there is a stable 2 cycle. It alternates between 2 values, namely -1 and 0. So, there is no fixed point, but periodic behavior, which we have seen even in case of integers. So, analytical treatment is this. We take the map of a map, but that is too much of calculus, let us forget it. So, 2 cycle fixed points are 0 and -1, 0 and -1, and these are the fixed points of the one cycle. Something fixed point of a one cycle obviously will be fixed point of 2 cycles. Both of these are stable. 2 cycles fixed points are stable. 1 cycle fixed points both were unstable. So, it showed a periodic 2 cycle behavior. Now, I have just changed x k square minus 1 to 2 x k square minus 1, a little change, and let us see what happens. 2 fixed points are this, both are seen to be unstable because it is 4 x k. If you take the derivative 4 x k, 4 times this is minus 2, 4 times this is 4. So, both are seen to be unstable. Not only that, however, 2 cycles, you will see this fixed points are the roots of this, and again you will see 2 cycle fixed points are again unstable. Not only fixed points are unstable, 2 cycle fixed points are also unstable. That means no 2 cycle periodic behavior. Then what happens? If both are unstable, so as I said, I believe my calculator more than my analytical ability. So, I start with 0.321 and 0.322 and carry on these iterations. There is no -1 0 -1 0 because 2 cycle periodic behavior was unstable. And what we see that I started with a very little difference 0.321 and 0.322, but after 14 iterations one has gone to 0.925, other has gone to -0.926. And if you remember, the range was from -1 to +1. So, if I commit an error of 0.001 within 13 iterations, one is saying sunny weather, the other is saying, oh, that will be very storm, huge storm, do not go out. That is the weather prediction. I mean, when they say today will be sunny, you definitely take your umbrella, right? No periodicity, no pattern, number changes in a haphazard way, and this is what is called chaotic behavior or chaos. And the most important thing is this sensitivity to initial condition. If there is a little change in the initial value, you are not sure about your iterations very soon, what result you are getting. They are useless results. Well, intense sensitivity to initial value, which is called butterfly effect, because once somebody said butterfly effect because as if the butterfly flaps its wing in Brazil, there will be a tornado in Siberia, because that will change the initial conditions a little bit, and after some time weather will be totally unpredictable. Actually, this is not the first time people became conscious of huge effect of a small input change. That was most beautifully explained by Pascal, Blaise Pascal, French genius. He said, Cleopatra's nose been a little flatter, the world history would have been different, because then there would not have been any Roman Empire, Roman Republic would have continued. Mark Antony would not have chased Cleopatra and leaving his fleet in disarray. He would have won, he would not have lost, and Augustus would not have created the Roman Empire. So, had Cleopatra's nose been a little flatter, that was Pascal said that a small input change can have drastic effect. And this is what we can show now, that we take a double pendulum. that a pendulum attached to another pendulum. There is two hinge rod. There is one rod and another rod. So, with some initial energy, it will be in the non-chaotic range. That means, if you have little change in the initial conditions, subsequent oscillations will be not differing much. Because if I want to start exactly, I cannot do it exactly with I estimations, so initial conditions are a little different. But you will say the subsequent oscillation also will be little different. Then I will go to a regime, initial energy is such that the oscillation is chaotic regime. That means a little change in initial condition will immediately destroy the oscillation and behave very differently. I hope it comes. This is in the non-chaotic regime. You see, two subsequent oscillations are very similar. I started with I estimated same initial conditions like this. Because it is in the non-chaotic regime, subsequent oscillations is periodic and a little differing a little bit. And now we will start from a regime when it is in the chaotic regime. So, a little change in the initial conditions will create very different oscillations. Because we started almost with similar initial conditions, but very soon it became totally different. Because there is damping in the system, so we can't see it for very long, maybe once more. Right, this is what has to be seen. Immediately they go away from each other. So, what we have seen that xk square minus 1 and 2xk square minus 1 behave very differently. With lambda 1 there was no chaos, with lambda equal to 2 there was chaos. So, this parameter dependence is important. For some parameter, it like the energy, initial energy in this pendulum case, and the map which has been studied most is this, which is known as logistic map. Lambda xk into 1 minus xk, lambda is restricted within this range 0 to 4, so that xk lies within the range 0 to 1. And here, well, fixed points one can see, and this is the lambda. Up to 1, the fixed point is 0. As lambda crosses 1, the fixed point changes, but there is only one fixed point. Then when lambda goes to 3, it becomes a 2 cycle. That means it oscillates between this value and that value. Whatever may be the starting value, after large number of iterations, the iterations oscillate between this value and this value. Then here, it starts a 4 cycle periodic behavior. It goes from here, there, then there. Or I do not remember, it may be the other way around, from here to there, then there, then there, then there. But it oscillates between these 4 values. Then it goes, 8 cycle, 16 cycle, and all that, ultimately it becomes chaotic. This is the values of lambda. At 3, it became fixed point to 2 cycle. Then at this value of lambda, 2 cycle to 4 cycle, 4 to 8, and the corresponding values of lambda. And these values of lambda, it has gone no cycle, no period, aperiodic, chaotic. That means value is never repeated. So that is called chaos, one root, that is called period doubling cascade route to chaos. Now, this is that 3.57 approximately, period doubling route to chaos, and this is seen in lots of various fields. in fluid mechanics, lasers, electronic junctions, mechanical oscillators, chemical reaction, share market, what not. This period doubling root to chaos has been observed. And that gave rise to the new paradigm of science, which is called chaos. At these chaotic stages, the iterates never settle, cover infinite points, but do not fill up a line segment. Such attractors are called chaotic attractors with some fractional dimensions, which I will come a little later. Finally, for lambda equal to 4, the whole line 0 to 1 is filled up. Now, one thing to note that this little rectangular portion, if we blow up, this is from 3.847 to 3.85. This is this region. If you expand, zoom, you see it looks like this. And there is a little similarity between this picture and that picture, as if it has been inverted. And if you take a little, and if you take a little zone here and then again zoom, you will see this picture. That means this is such a set of points where there are regions which look the same at every scale, and that is what is now called fractal. So, another thing is period 3 implies chaos. This is a Sarkowski's theorem that if you see period 3 in any iteration, then you must have seen these cycles. Now, let us go into these fractals, which objects which are self-similar at all scales. These are mathematical fractals. And fractals in nature, we see lots of places, streaks of lightning in the sky, branching of trees, cloud outlines, wall cracks, hillside skyline, fern tip, cauliflower. This is the best example of fractal. If you look a small piece of cauliflower under a microscope, you think you are looking at the whole cauliflower. The cauliflower, every flower looks similar at every scale, and similarly the coastline. So, now let us go from real number to the iteration in the field of complex numbers. So, a solution of Z4 equal to 1. This we want to solve by Newton's law, Newton's method. So, assume Z1 and continue the following iteration. We have seen this Taylor's expansion. Then you start from any Zk, next iteration you get this, you only need the derivative of this at Zk. So, the roots is answer is known, +1, -1, +i, -i. But if you take the initial conditions Z1, then this is the picture we get. All these values of Z1 will give you +1. All these values of Z1 will give you -1. All these values of Z1 will give you +i, and all these values will give you -i. But look at these 45-degree lines. A little change in the initial guess will take you from this root to that root, or from this root to that root. And as you see beautiful pictures, they look very similar. This is really the fractal basin boundaries. These are the fixed points, and their basins of attraction, these are the boundaries which have fractal nature. And how was it found out? With a real surprise for a maths teacher, he gave a home assignment, and then he realized this is the thing. He expected that it will be as simple as only 4 colors, but this intermixing of the boundaries came as a surprise. So, the most famous iteration in the field of complex number is this. This is a complex constant. So, we talk of white holes, that means starting points which take iterations to infinity, and discrete set of infinite points which continuous range for real numbers. Here, discrete set of infinite points. For complex numbers, concentrate on the boundaries of white holes. The boundaries can be, nature of it is depend on both the parameter c and the initial value of z. So, the set of all points on the boundary between the prisoner set where it does not go to infinity and the white holes are called Julia set, which may be connected or disconnected. So, this is the disconnected Julia set for these values of C, and for this value of C, Julia set is connected. And concentrate on the connected Julia set for which values of the parameter, and this values of C in the complex plane producing connected Julia set gives us the Mandelbrot set. So, this is the famous Mandelbrot set. The values of imaginary part of C and real part of C for which this does not go to infinity, these are the prisoner sets. And look at the boundaries. Actually, the black region is the Mandelbrot set, but the boundary of the Mandelbrot set shows real fractal, borderline fractal. This magnified region is here. Similarly, this magnified region is here, and you can still see this, a cardioid kind of shape with a circle and a smaller circle like this at every scale. This is magnification of 10 to the power 4 times, I think. If you magnify it even more, I still continue to see that. And this became a computer generated painting. There are books on this, beautiful pictures with the complex number iterations. So, mathematical fractal and fractal dimensions, let us say I define a geometric process. I take an equilateral triangle, and for every side I rub the middle 1/3 and create an isosceles triangle. This is the same side, this. I do it for the 3 sides. Then I keep on doing that. Erase the middle 1/3 and create this, middle 1/3 and create this, we get this star shape. If I continue forever, I get this at infinite steps. So, at every step you see the perimeter is increasing by a factor 4/3. Length of this is 4/3 times this. The same thing will happen here. Length of this and length of this is 4/3 times that. So, the perimeter is increasing at every step by a factor 4/3. So, the perimeter after infinite step is infinity. So, the perimeter of this curve, I mean I cannot draw it after infinite steps, that mathematical object whatever it is, the perimeter is infinity, but it encloses a finite area. So, that is not the curve that we are commonly encounter in geometry. A closed curve must enclose a finite area, but the length of the closed curve is also finite. But here this curve is funny that it is continuous everywhere, but differentiable nowhere. And the area with unit side at k equal to 0, the area finally will be this, which is very much finite, whereas perimeter is infinity, and that is known as Cock Island. So, boundary is more than a curve and less than an area. So, we have to now talk of this kind of curves dimension. It is, as I said, curve is continuous everywhere, differentiable nowhere. Weierstrass created such function, and closed self similarity of such functions can be seen. If I plot this function is summed over infinite terms, but only 10 terms if I take and plot the function 10 terms x from 0 to 1, this is the function value. And now I am plotting again 10 terms, but from 0 to 0.1, this 0 to 0.1, this range, I only magnified it, looks very similar, only with 10 terms. So, here comes the fractal dimensions, that how do I define a similarity dimension, that if this is a line of unit length and if I have a unit length, then I need 1 stick, but if I have a stick, my measure as epsilon, then I need 1 upon epsilon number of sticks to cover all the points. Similarly, for the square, to cover the entire square with the smaller square, I need 1 upon epsilon squared number of squares, and for the cube I need 1 upon epsilon cube number of smaller cubes. So, if the length scale is epsilon, the number needed to cover the entire set varies as this: e to the power 1, e to the power 2, e to the power 3, dimension is 1, 2, 3. So, I define similarity dimension as n into e to the power ds equal to 1. keeping it to the normal Euclidean dimension. So, for this Cock Island, if the dimension is 1/3, epsilon is 1/3, we get 4 sticks. Instead of 1 stick, I need 4 sticks. So, epsilon is 1/3, n is 4. So, the dimension of this entire curve will be 1.2618. It is neither 1 not 2, it is more than 1, less than 2. It is a fractal dimension. So, similarly, there are lots of objects mathematicians have created: Sierpinski gasket, Sierpinski carpet, Menge sponge in 3 dimensions. You can see the dimensions, it is more than 2, less than 3. It is not having a volume, but it is infinite surface area. Now, fractals in nature, as I said, the coastal line of any country, what is the length? The question is wrong. Such a curve length does not mean it will depend on what scale you have used. Have you taken a meter stick, or you have taken a 100 kilometer stick, or you have taken a millimeter stick? The answer will depend on that. Normally, a curve length will not depend what scale you are using. So, ultimately, we see how many boxes are needed with various length scale, and the slope at the upper end, this is 1 upon delta. So, delta is smaller the length, this is the slope defines the similarity dimension ds. This is one way, there are different measures, lots of measures. So, west coast of Britain. So, what is the coastline of Britain? That question came, but it cannot be answered because it is so kinky. If it is almost kinky everywhere, so the coastline of Britain has dimension 1.25, quite more than 1. Whereas, tip of South Africa, which looks very smooth, not so kinky, because the dimension is only 1.02, very close to 1. Now comes the big question. So, whatever we are happening in nature, we can explain it in terms of chaotic behavior and fractal dimension, all that. So, is that the correct description or correct route to describe the nature? Some people believe yes, but some people believe the other way around. He said no, nature does not follow differential equation, nonlinear differential equation give you fractal and all that. Nature follows very small programs, if else. So, there is an approach cellular automata, that if this then this, if this then this. So, what is happening? One starts with lots of dots, then defines such very simple rules, that if there is a dot here, where should be the next dot, and following that cellular automata, you see fun tip has been generated. So, did nature follow this route to give you the final fun tip, or the fractal dimension of this? That is how nonlinear phenomena can explain nature. So, the answer is obviously not known, it is 2 groups. Thank you.